Welcome to the fourth unit of cellular and mobile communication. Today's topic is cell site and mobile antennas. So today we will learn sum and difference patterns of antennas and their synthesis. We will learn about omnidirectional antennas, directional antennas for interference reduction, then space diversity antennas, umbrella pattern antennas, minimum separation of cell site antennas, and high gain antennas. So let us start with cell site and mobile antennas. In cellular system, we know that the antennas are not only used to radiate or receive signals, rather they are used to control three aspects. First aspect is coverage, that what is the area that can be covered, that is coverage. Second is called interference. So how to manage interference between cells, and capacity. So capacity indicates how many users it can accommodate. So coverage, what is the area that it can covered? Interference management, how well it can manage interference. And third is capacity, or how many users it can accommodate. Now in cell site antenna is some antenna placed at the base station. This type of antenna may be omnidirectional, it may be directional, it may be sectorized, it may be diversity based, or umbrella pattern type. So this is all about a cell site antenna or antenna placed at the BTS, base station antenna, or BS. Mobile antenna, or the antenna that is mounted on the mobile station or cell phone, whatever you say. So this is mounted on the vehicle or handset. It should receive signals from different directions because the mobile user may move. Okay. So as the mobile user have a mobility, so it is traveling from one place to another place. So that is why the mobile station should receive signals from different directions. For mobile units, the device that is vehicle, a roof mounted antenna is always preferred. So for vehicles, you must have seen that some antennas are mounted on the roof. So the roof mounted antenna gives better performance than a lower glass mounted antenna. So whenever we are carrying a mobile phone, it may not be feasible for us to place the mobile phone on the top of the vehicle, right? Because we are sitting inside. So for mobile devices, this is not applicable. For other mobile applications, suppose one car is being communicated from a base station. So for such cases, it's always preferred that the mobile antennas should be mounted on the top of the vehicle. Now, to receive a high strength signal, it's always preferred that mobile antenna has a high gain. Okay. But what happens if the mobile antenna beam widths are very narrow? So suppose earlier it was, the beam was like that. Okay, drawing the. So suppose in one case, the beam is like that. And when we increase the gain, so the beam narrows like that, narrow down. So in such case, what happens? Here the beam width is more. So this is less directional, but here the beam width is less. So this is more directional. So we use directional beam to reduce interference. That is true. But if the beam width is very thin, I mean, for making the gain high, then what will happen? It can only receive or transmit signals through a very narrow aperture. So if the aperture becomes very narrow, and as a mobile transmission is not a directional communication, so it is an inherent multipath communication. So what happens? Suppose an antenna is using very narrow beam. So suppose after multipath reflection, some mobile signal enters the receiver through this location. So it won't be able to receive the signal because there is a null in the radiation pattern of the mobile receiver. Whereas if the beam width is more, so after reflection, if the same signal penetrates through this region, then it can be received because there is no null in this area. So that is why when we will be planning to use a very high gain antenna in mobile station with mobile station, then we need to use very carefully because when the gain becomes high, so the main radiation will be towards this horizontal. So vertically, it won't be able to receive any signal, or the receive signal amplitude will be so less that it will be detected as a noise. So we must be careful. Now let us come to this topic, the sum and difference patterns and their synthesis. So what is sum pattern? What is difference pattern? So basically sum and difference patterns are associated with antenna arrays. So what is antenna array? Antenna array means when more than one radiating element are connected in a specific manner to alter the radiation pattern of the antenna. So that is the main goal of antenna array. Primarily, antenna array is used to increase gain. But what will be the pattern of the antenna array? That is completely based on the signal strength and also the phase difference between the signal that is being given to the antenna elements. So, in this figure, if you can see, this is one antenna, this is another antenna. Okay. So this is one antenna, this is another antenna. Now these antennas are separated by a distance d. Okay, so two identical antenna elements are separated by distance d. So it is very important that these antenna elements must be identical. It is very important. So in this case, if the phase difference of the signal that is being given to the antenna or the two antennas are excited with the same phase signal, then their pattern will be added in phase and we get a very high gain pattern here. Okay. But if I take the same two identical antennas, but I excite the two antennas with two signals, those are completely out of phase, or if their phase difference is 180-degree. So what happens? You can see that unlike the first case, there is a bore sight null. Bore sight means along the main direction where the antenna is intended to radiate. But in this case, we are getting a null in the bore sight. Null means very low amplitude. So this pattern is called sum pattern. This pattern is called difference pattern. So you can see that in the sum pattern, there is one main lobe, and along with that, there are some side lobes as well. In between main lobe and side lobe, there could be nulls. But this null will not ever occur in the main line of sight or bore sight. However, in difference pattern, what happens? This null will be created in the bore sight itself, and on either side of this null, there could be some high gain lobes. So based on my requirement, I can use any of these feeding techniques or phasing techniques where I require a complete directional beam to illuminate one cell. I will be using this case. But where the scenario is, I don't want to illuminate the central position, rather, I want to illuminate the two side portions, then I'll be using this difference pattern. Now let us come to the equation. Due to that, these patterns are getting generated. So this is an example for a two-element array. This is a basic array. And we assume that the signals that are being fed to those antenna elements are actually having equal amplitude, but some phase that is denoted by beta, or the phase difference that is denoted by beta. So this psi is equal to kd cos theta plus beta. That is the governing equation. So psi, that is the phase difference between elements in radians. K, you know that this is called phase constant, or 2 pi by lambda, and the unit is radian per meter. The d is the spacing between the two antennas. So if I can see this diagram, so these two antenna elements were uh, at a distance of d. So this is called the spacing between the two elements, antenna elements, and the theta is observation angle. Beta is progressive phase shift in radians, and lambda is the wavelength in meter. So for the sum pattern, this pattern equation will be 2E0 cos psi by 2. And for the difference pattern, this should be 2E0 sin psi by 2. So you need to remember these two equations. This is the sum pattern equation. This is the difference pattern equation. Now let us solve some problem. So what is the problem? So E0 is equal to 1 and psi is equal to 60 degree. Find the sum pattern and difference pattern. So first we need to convert the angle to radians. Okay. Or if we can start with the degree mode, that is also not a problem. Just we need to use it consistently. So this psi by 2 is equal to 60 degree by 2 is equal to 30 degree. So now if I want to calculate the sum pattern, So the E sum, that is 1.732, or this is the peak value of electric field at the center of the bore site. However, if I follow this equation 2E0 sin psi by 2, then this is the difference pattern, because you see that the difference signal E difference is equal to 1. So 1.732 is more than 1. So if I plot the central electric field level, uh, so definitely the sum pattern has, I mean, this value is higher than this difference pattern. Now let us come to the omnidirectional antennas. So omnidirectional, as the name suggests, omni means everywhere. Okay. So omnidirectional antenna radiates almost equally in all horizontal directions. So where this type of radiation is important, so you know that suppose I have only one antenna placed to be placed at the center of the cell. So from the center of the cell, the radiation should reach to all users I mean, who are there in the cell using the services, cellular mobile services. So for that, without any specific planning or targeting any zones, if I simply place one horizontal antenna, so power will be reaching to all users in the cell. But there is a problem also, because if the radiation is omnidirectional, so the radiation will cross the boundary, because when an antenna radiates, it radiates up to infinite theoretically. So if it radiates from the center of the cell and it reaches, the radiation reaches some cell which are either having the same set of frequencies. So for this, there will be some interference that is called co-channel interference, or the radiation will reach to the adjacent cell where it will contribute to adjacent cell interference. So though the antenna are very simple for coverage, it is not so good to handle interference. So in the figure, you can see that this is one omnidirectional antenna and it is radiating some energy horizontally. Now, there could be three types of omnidirectional radiation, because the omnidirectional radiation remains in one plane, but the radiation characteristics in other planes should also be taken into care. So in the first place, you see, if you see the elevation pattern cross section, so there is a figure of 8 type lobe. The beam width is not that much narrow. So majorly it covers the horizontal area, but it covers some area that are 45-degree at an elevation of 45-degree angle from the ground as well. So it covers that area as well. However, if I increase the gain of such omnidirectional antenna, so the antenna now confines more energy towards horizontal, and in the vertical area, the coverage gets reduced. So from a thick donut shape, you know that omnidirectional means the donut shape. So from a thick donut, it becomes a thinner donut. Another shape could be that are mainly used for our umbrella pattern. So whatever you can see in this diagram, actually this is a reverse umbrella pattern. So in this case, it also have a horizontal coverage, but the energy is not necessarily going perfectly horizontal, main energy. So the main coverage is slightly downward. So these type of antennas or antenna radiation patterns are preferred where I want to cover some area to some extent, but I want that the radiation does not reach long or it does not reach so far. So three types of omnidirectional radiation pattern I have discussed. So for ideal horizontal coverage, this azimuth coverage should be 360 degree. Now, if the total available channels are S and cluster size is N, then the channels per cell should be S divided by N. So this is a simple calculation that my antenna is radiating in all direction. But if I have my available channel number and cluster size, then I can calculate the number of channels per cell. So let us take one easy example. So suppose S or total available channels are 420 and N or cluster size is 7. So find the number of channels per omnidirectional cell. So we know that the formula is M is equal to S divided by N. So finally, the channels per cell, that value comes up as 60 channels per cell. So simple division, very easy to calculate, where the antenna radiates in all directions. But we have the idea that the omnidirectional radiation pattern is not useful if the concern is interference, because the omnidirectional radiation reaches or covers the area uh, for an infinitely, the coverage is infinite around the antenna. So that is why we need some directional antennas as well. So first technique is called sectoring and second technique is called umbrella pattern. What is sectoring? So sectoring means, suppose if I have a hexagon, so I will make such an antenna that will have a 120-degree beam width. So that what will happen? Three antennas can cover these three sectors. Okay, so this is called sectoring. So this is a hexagon. So I can divide this 360-degree radiation angle into three equally spaced sectors. Each sector is actually covering 120 degree of its area. So if three antennas I can use, then three antennas, each of the antennas will take care of its own sector with a 120-degree beam width. This is called three sector cell. In the same manner, I can use six antennas if each antennas are having 60-degree beam width. Then by six antennas, the total 360-degree coverage can be obtained. Now, whenever I'm limiting that the beam width is 60-degree or 120-degree, it means that the radiation is not omnidirectional anymore. Rather, the intended direction of radiation or intended angle of radiation is specified. So this is one technique of using directional antennas for interference reduction. And this technique is called sectoring technique. Another technique is called umbrella pattern technique. So umbrella pattern means the radiation pattern will be modified in such a manner that it will cover the cell towards horizontal to some extent, but ultimately the radiation will not go outside the internet cell, because the main radiation will be towards a bit tilted towards down, okay, towards a down angle. So that is why more energy will be focused towards the ground in the nearby area of the cell tower, and less energy towards the distant area. So strategically, we need to modify that. So we have learned in earlier modules that if I take a monopole antenna and place a disc on the top of that, then the horizontal radiation pattern changes, because the radiation gets reflected by the small disc, the upward direction, and it comes back. The radiation comes back, and a significant amount of energy is focused towards the ground. So this is called umbrella pattern technique. Now let us do some easy problems on sectoring. So for sectors per cell, that we need to calculate. So if theta S is the sector angle, or the angle that an antenna can cover, or the antenna beam width is theta S, then this is the sector angle. And suppose what is the number of section is ns. So 360 degree divided by ns. So that is why if I take this example, 3 sectors, total angle is 360 degree. So 360 degree divided by 3, it means 120. So if I want to divide the entire cell into 3 sectors, then I need to use such an antenna which would have a beam width of 120 degree. Similarly, if I want to divide this entire area or entire cell into 6 sectors, so the antenna that I need to use should have the beam width of 60 degree. So now let us take an example. A cell is divided into 3 sectors, 120 degree. A cell is divided into 6 sectors, 60 degree. Now co-channel reuse distance. So co-channel reuse distance is Q is equal to root over 3n and D is equal to QR. So these formulas we have already studied, but for the sake of this module, we are revising that. So what is Q? Co-channel interference reduction factor. We have a detailed lecture on that. N is cluster size, D is co-channel distance. It means the distance between center to center distance between two co-channel cells. And R is cell radius. So suppose I have a 7-cell system. So 7 cell, it means the value of N is 7, or the cluster size is 7. So the value of Q is equal to root over 3 into 7, or root over 21, and that is 4.6. So that definitely D should be equal to 4.6 R. So let us take another problem. Suppose the cluster size is 7, R is equal to 2 kilometer. Now find Q and D. So first we need to calculate Q. So Q is equal to root over 3n. So 4.58 or near to 4.6. I would recommend that keep it 4.58 only. Don't make it 4.6. Then you should calculate D. So D is equal to QR. So 4.58 into 2 kilometer. That is 9.16 kilometer. So by remembering such small equations, you will be able to solve many easy problems. Now let us come to the topic of space diversity antennas. So what is space diversity? So we have the idea that compared to the fixed point or point-to-point communication, the mobile radio communication is very unique. Why is it so? Because the mobile radio communication depends on multipath communication. And when there is multipath communication, so the fading occurs, because when multiple reflected waves combine destructively or at the opposite phase, so then their signal strength gets reduced, and this is called fading. So if my mobile device uses only one antenna, so signal may be weak. When it's weak, so the communication will get hampered, because due to destructive interference, suppose I am standing in at a place, and due to some buildings that are located outside my house, so the destructive interference is happening in such a way that I am getting very low signal. So one possible solution could be, if I change my position, and I can try that whether my signal strength gets better. But it might not be possible all the way. Then what is the solution then? Solution is use another antenna. Okay. So without moving myself, okay, I mean, or the mobile devices, I can place another antenna. This type of antenna system is called space diversity antenna system. Two different antenna kept at a distance. What is the logic behind that? The logic is, if they are kept at a distance, then the probability of getting fading at the both receiver at the same time is very low. So now let us look at the structure. Uh, how does it look like? So two receiving antennas are there, and they are separated by a distance, that is S. Now, if one antenna is in fade, the other antenna may receive a stronger signal. So that is why we connect one combiner to these two antennas, and finally we get the signal at a receiver. So we have already discussed this combiner is nothing but a power divider. It could be a T-junction power divider, it could be Wilkinson power divider, and there are other types of power dividers as well. Now the minimum separation that is followed for this diversity reception, so the minimum separation is 8 lambda. Now if I ask you that, please calculate lambda for this. So suppose 850 megahertz. So F is equal to, say, 900 megahertz, for example. If F is equal to 900 megahertz, then what will be lambda? Definitely this should be C by F. So 3 into 10 to the power 8 meter per second divided by 900 into 10 to the power 6. So this will be the wavelength in meter. The unit is very important. Don't make mistake in unit. So 10 to the power 6, 10 to the power 8, 10 square. So this is actually 300 divided by 900. So 3 by 9 meter, or 1 by 3 meter, or 0.33 meter. So for a diversity reception, to minimize the probability of getting faded signal, I need to keep the two antenna elements at least at a distance of 0.33 meter. Okay. Well, now let us move to the next topic. that calculation already I have shown, so I'm not going into that. So remember that S minimum or the minimum distance, that is 8 lambda. If in the question paper, suppose 8 is not given, some other figures are given. So the general equation is S min or the minimum distance for spacing or minimum distance for separation is equal to n lambda. N is number of wavelengths and lambda is the wavelength. So suppose the question is at 850 megahertz, if the lambda is 0.353 meter, then what is the approximate separation? So 8 lambda, it means 8 into 0.353 meter. So the answer is 2.824 meter. So now let us discuss umbrella pattern antennas. So umbrella pattern antenna means it directs more energy towards the nearby cell area and reduces radiation towards the distant regions. In these umbrella pattern antennas, there is some design equations. So for a height h and horizontal distance d, this theta is equal to tan inverse h by d. And this theta means the elevation angle of the umbrella pattern radiation. So suppose h is 16 kilometer and the d is 160 kilometer, for example. So what is the elevation angle? So elevation angle is 5.7 degree. This will be tan inverse 0.1. So 5.7 degree. It means what? Even if the upward radiation is very small, suppose here the upward radiation is only 5.7 degree, but it may contribute to long distance interference. Now the minimum separation of cell site antennas. So this is also same. That should be greater than 8 lambda. So already you know that. That first we need to get the frequency f. From this frequency, you need to convert it to lambda. So lambda is equal to c by f. So already that calculation I have shown. So now the separation is 0.333. So the lambda is 0.333. So the separation should be 2.664. 8 into 0.33 means 2.664 or 2.66 meter. Okay, so I believe that that aspect is very clear. So now high gain antennas. So high gain antenna, what is the role of high gain antenna? Means high gain means from a specific direction, it can receive a signal in a better manner or towards some specific direction it can throw power. That is called high gain antenna. Now at a cell site, high gain directional antennas can improve the coverage in a selected sector and definitely it will reduce unwanted radiation. But for a mobile unit, high gain should be used very carefully because already I have told that in mobile phone, high gain antenna, what it happens that it compresses the radiation pattern vertically. So I've given 3 examples of 3 types of omnidirectional low gain and high gain antenna. So basically omnidirectional in one plane only. So only horizontal plane is omnidirectional. But the vertical plane is not like that. So in the first example, that was a normal figure of 8 elevation pattern, but the azimuth pattern or horizontal pattern is perfectly circular. But in this case, what is happening in the second case, this is a high gain antenna. So if you can see in the horizontal direction, the powers are confined. However, in the azimuth pattern, we can see that uh, there is a horizontal coverage. So this is a high gain antenna. So if the mobile antenna gain is so high and after multiple reflection, the signal comes to the receiver through some vertical angle. So there will be issue in reception, because if I use high gain antenna at the receiver, then what will happen? It won't be able to receive signals from all directions. So we should be very careful while we plan to use a high gain antenna for receiver. For transmitter, it's okay, no problem. High gain transmission is desirable because I know that to which area or which cell I am focusing my power on. Okay. So this we need to keep it in mind that high gain antenna should be preferably used for transmitters, not for receivers. When the user is moving from here, this is also very important. Generally, for point to point, there is no problem. We can use high gain transmitter, high gain receiver, it will give benefit only. But for reflection based uh, communication system, okay, because point to point communication system is not reflection based communication system. This is free space communication system. So that is why in both sides, I mean, on the both sides, if high gain transmitter and receiver are used, there is no problem. That is desirable. But for a reflection based communication system, at the receiver side, we cannot use high gain antenna. Anyways. So what is the benefit of higher gain? So benefits are only related to transmitter side only, because it will extend coverage in desired direction. In the unwanted region, it will not focus. So in the other direction, it will have low interference. Now two scenarios. Suppose we have a car and we need to mount the antenna. So where there will be higher gain. So roof mounted antennas will be having higher gain, and the glass mounted antenna will be having lower gain. So the key factor is, already we have discussed in the last class, that for the receiver side, by changing the height, antenna height, we can have a difference of 3 dB. So if I double the height, then we will get a 3 dB more gain. Okay, if I make the height half, then I will have 3 dB less gain. Okay, so that is why for roof mounted antenna, we are getting 3 dB more gain. And for glass mounted antennas, we are getting 1 to 3, 1 dB gain around. Now, when the antenna gain is more, so it confines radiation towards a specific direction. So that is why if you can see this figure, so this power confinement is very narrow, but the power level is very high. On the other hand, if you look at this figure on the right hand side, so here the power confinement is not that much strong, but and also the power radiation level is very low. So for transmitting side, we can use this high gain mobile antenna, and for receiver side, we can use this low gain antenna. Now, what is gain in dB? So basically, if the gain in linear scale is known, so if the linear gain, for example, is 2, and we need to find the gain in dB. So the formula is 10 log 10 of this G linear. Or 10 log G linear base 10. In this way also we can say. Now if you substitute the value, so 10 log 2 base 10, that is 0.3. If I multiply it by 10, then it becomes 3 dB. Now let us come to some parameter that is related to EIRP. So that is effective isotropic radiated power. So effective isotropic radiated power is equal to transmitter power output power in dBm plus antenna gain in dBi minus cable or connector loss. So this formula we need to remember that what is EIRP or effective isotropic radiated power. So for example, it is given that the transmitted power is 40 dBm. The gain of the antenna is 12 dBi and the loss is 2 dB. So PT plus GT minus L, that will be 50 dBm. So we have discussed about a lot of antennas. So now let us make a summary of that. So first antenna that we discussed is omnidirectional antenna. So the main coverage is 360-degree horizontal radiation. It's very simple to design, simple to install, and for coverage that is great. But the limitation is interference. Then comes directional antenna. So it is having narrower beam, so it is able to focus power towards some designated area, not any unintended area. So directional antenna is better for interference control. Next comes space diversity antenna. Space diversity antenna reduces fading, but multiple receivers are used in space diversity antenna. Umbrella pattern antenna. Umbrella pattern antenna is a strategy to shape the antenna radiation pattern towards the ground while maintaining a minimum coverage that is just enough to coverage the horizontal position of the cell. So the local coverage will be ensured, but the long distance coverage will be restricted. And in this way, we can reduce the interference problem. Then high gain antenna. So high gain antenna is a preferred solution for transmitters in cellular mobile communication. But we should be careful about using it in receiver, because for a receiver that is dependent on multiple path communication. So if you use very highly directional antenna, so after multipath reflection, if the power comes or the signal comes through some regions where your antenna does not radiate, then it will be problematic for signal reception. And for vehicles, two type of antenna, what is mobile roof mounted antennas and glass mounted antenna. Mobile roof mounted antennas are actually having better gain compared to glass mounted antennas. So let us make a quick summary of today's session. So first is cell site and mobile antennas are central to cellular system design. Omnidirectional antennas provide 360-degree coverage, but they may create more interference. Directional antennas divide a cell into sectors, and they reduce co-channel interference. Sum and difference patterns that are created using array. So for different types of beam shaping based on the real requirements, the sum and difference patterns are created. Space diversity antennas are used to reduce fading by separated receiving antennas. Umbrella pattern antennas are used to confine energy close to the cell site, and they help reduce long distance interference. Finally, we have learned that minimum antenna separation is required to reduce pattern ripple and preserve diversity performance. So this was all about Unit 4. We have touched all the points mentioned in the syllabus, and with the help of theory and equation, we have covered each and every points that are important. Thank you so much for attending the session.